The topic is dividing whole numbers. The objectives in this topic are divide whole numbers, perform long division, solve applications that require dividing by whole numbers, and find the average of a list of numbers. The process of separating a quantity into equal parts is called division. And let's break down a division problem the same way we've been doing with addition, subtraction, and multiplication. We call the first number, the thing to the left of the divided sign, the dividend. We call the thing we are dividing by, the thing to the right of the division sign, the divisor. The dividend divided by the divisor. And we call the answer to a division problem the quotient. Now, just like sum is what we call the answer to an addition problem, difference, subtraction problem, product, multiplication problem, quotient is what we call the answer to a division problem. And a division problem is just a multiplication problem waiting for you to fill in the blank. So remember that multiplication table you made. What times 6 is 24? 4 times 6 is 24. And now you've divided 24 divided by 6. It gives you 4. In fact, this multiplication problem would also give us another division problem. 24 divided by 4 is 6. The fact that 6 times 4 equals 24 in any order means 24 divided by 6 is 4, and 24 divided by 4 is 6. And there's a lot of ways to write a division problem. 24 divided by 6 equals 4 is the same as 24 over 6 equals 4. This division bar, fraction bar, means division. First divided by second is the same as top divided by bottom. And it's also the same as inside divided by outside equals the number on top. These are 3 different ways to show 24 divided by 6 equals 4. We're going to write everything in this inside divided by outside form. And we're going to take things 1 digit at a time, as we often do. Ask yourself, how many times does the thing on the outside go into what we have on the inside? How many times Price is Right rules, as close as you can get without going over? How many times does 5 go into 7? Just once. Because twice would be 10. That's too much. It goes over. You lose the showcase. Once you know it goes in 1 time, you write that on top, and then you multiply around the corner. 1 times 5 is what? 1 times 5 is 5. And then you subtract. 7 minus 5 is 2. Then you look at the next number, you bring it down, and you do it again. 5 goes into 20. How many times without going over? 4 times. Multiply around the corner. That 4 you just wrote times 5 is 20. We subtract and we get 0. Oh, I'm so sorry. There we go. The 4 times the 5 is 20. 20 minus 20 is 0. There's no other numbers to bring down. We have nothing left over. So the answer is 14. And we can check that by multiplying. 14 times 5. 5 times 4 is 20. Carry the 2. 5 times 1 is 5. Plus 2 is 7. 70. Boom. Check by multiplying, just like subtraction can be checked by adding. What if we would have had something left over here? Well, that would be called a remainder. Here, the remainder is 0 because there was a 0 left over when we had nothing else to bring down. Before we get into remainders, let's look at some quick rules. We have some special division properties for the number 1, namely any number divided by itself equals 1. So 8 divided by 8 equals 1, 6 divided by 6 equals 1, and 4 divided by 4 equals 1. That's the 3 different ways we can see division. Likewise, the quotient of any number and 1 is that same number. So a number divided by 1 is itself. 8 divided by 1 is 8. 6 divided by 1 is 6. 3 divided by 1 is 3. 0 divided by 1 is 0. Why does 0 get to be another example more than the 3 that we showed for the first one? Well, it's because 0 itself has some special properties. The quotient of 0 in any number except 0 is 0. So if 0 comes first, 0 divided by 8. If it's on top, 0 divided by 6. Or if it's on the inside, 0 divided by 4, the answer is 0. That would include 0 divided by 1 from the last slide. On the other hand, the quotient of any number in 0, 0 coming second in the order, is not a number. We say that that would be undefined. 3 divided by 0. 3 divided by 0. 3 divided by 0. 3 divided by 0. We cannot divide by 0. The answer is undefined. So now we're going to, excuse me. So now we're going to find the quotient of 78 and 5. We write that 78 divided by 5, and we're going to do a process called long division. We ignore the 8, and we ask ourselves, how many times does 5 go into 7? Just the 7. Don't worry about the 8 right now. 5 goes into 7 once, so we put a 1 above the 7. Then we multiply around the corner and subtract. 1 times 5 is 5. So we subtract 5 from the 7. 7 minus 5 is 2. Bring down the next number. Bring down the 8. Then we do the process again. This time, 5 into 28. 5 goes into 28 5 times, because 5 times 5 is 25. We put a 5 up top, multiply around the corner, and subtract. 5 times 5 is 25. 28 minus 25 is 3. We have nothing else to bring down, which means we are done at this point, and we say that the answer is 15 remainder 3, expressed with an R. 63 divided by 3. 3 goes into 6 how many times without going over? 2. Multiply around the corner. 2 times 3 is what? 6. Subtract, we get 0. We're not done though, because we bring down the next number. 3 goes into 3. How many times without going over? 1. That 1 you just wrote times 3 is 3. We subtract, we get 0. Nothing else to bring down. No remainder. $3,451 divided by 7. It's okay if you curve this a little bit. Well, 7 goes into 3 how many times? Well, 7 can't even get into 3 once, so let's move that over and talk about 34. 7 goes into 34 how many times without going over? Well, 35 would be over, and that's 5, so it can only go in 4 times. 7 times 4 is 28. Subtract 14 minus 8 is 6. Okay. Is that a remainder 6? No, we have something to bring down. So bring down the 5 and we go again. 7 goes into 65. How many times without going over? Well, 9 times 7 is 63. That's as close as we can get to 65. Subtract and we have 2. Are we done? Nope, because we have one last number to bring down. 7 goes into 21 3 times. And once again, 3 times 7, 21. No remainder. 493. So we get this process. We get this process over and over. But let's take a look at 364 divided by 8. 8 goes into 36 how many times? Well, 8 times 2 is 16, times 3 is 24, times 4 is 32, and that's as close as we can get because 40 is too much. Bring down the 4. 8 times 5 is 40. 8 goes into 44 5 times without going over. 5 times 8 is 40. We got a 4. We've got nothing else to bring down. So we just say R4. 45, remainder 4. How can we check this? Well, our answer, let's take the 45 and let's multiply it by the 8. Literally take our answer and multiply it around the corner, just like we do with the individual digits during the problem. 8 times 5 is 40, carry the 4. 8 times 4 is 32, plus 4 is 36. Well, that's not 364. The remainder gets added on. We got what we started with. We know we're right. Our answer, 45, remainder 4. This is where everything changes. 615 divided by not a 1-digit number, but by a 2-digit number. But we do the same thing. 41 goes into 6 how many times? 41 can't get into 6. That's foolish. Next, 41 goes into 61 how many times? Once. Multiply around the corner. 1 times 41 is 41. And we subtract. 61 minus 41 is 20. Are we done? No. We have another number to bring down. Bring down the 5. Now we need 41 times 1 is 41. 41 times 2. 41 times 1 is 41. 41 times 2 is 82. 41 times 3 is 123. 41 times 4 is 164. 41 times 5. Put that over here. 41 times 5 is 205. And I'll stop there for now because 205 is what I need. 41 goes into 205 5 times. 5 times 41 is 205. There's no remainder. And there's nothing else to bring down. We didn't need anything higher than 41 times 5, but maybe we would have needed times 6, times 7, times 8, or times 9. So whenever we're dividing by a 2-digit number or a 3-digit number, go ahead and multiply out times 1, times 2, all the way through times 9. So you can just look at it. Because dividing by a 2-digit number is the same process as dividing by a 1-digit number in terms of what we ask ourselves. $8,017 divided by 16. We're going to go ahead and write it in division box form. First, divided by second is inside divided by the outside. And since we're dividing by 16, we might need 16 times 1 is 16. 16 times 2 is 32. 16 times 3 is 48. 16 times 4 is 64. 16 times 5 is 80. 16 times 6 is 96. 16 times 7, 112. 16 times 8, carry the 4, 8, 9, 10, 11, 12, 128. And 16 times 9 is 4, carry the 5, 9, 144. So these are the possible numbers we might need to see how many times 16 goes into something without going over. For instance, here, 16 goes into 80 5 times exactly. So when we subtract, there's nothing left. Bring down the 1, we have to ask the question. 16 goes into 1 how many times? The answer is 0, so you have to put the 0 in. Bring down the next number. Why? Because 0 times 16 is 0. We subtract, we get 1, and then we bring down the 7. All that work, we didn't need anything except that 80. 16 goes into 17 1 time without going over. 1 times 16 is 16. Subtract, we get a remainder 1. Some keywords that tell us that we're looking at a problem that we have to solve by dividing are divide, quotient, divided by, divided or shared equally among, and per. Divide as in divide 8 by 4. That's 8 divided by 4. Quotient, the quotient of 64 and 8. 64 divided by 8. The order matters. Divided by. 12 divided by 4 is 12 divided by 4. Divided or shared equally among. We have $75 divided equally among 3 people. That'd be 75 divided by 3. And per 100 miles per 2 hours is 100 miles divided by 2 hours. Books are being packed 12 to a box. If there are 1,344 books to be packed, how many boxes will be used? So we're dividing equally, or we're trying to be equal at least. 1,344 divided up into sections of 12. So how many 12s are we going to need for 1,344? That's 1,344 divided by 12. And it does work out evenly. We set up 1,344 divided by 12. 12 goes into 13 once. 1 times 12 is 12. 13 minus 12 is 1. Bring down the 4. 12 goes into 14 once. 1 times 12 is 12. 14 minus 12 is 2. Bring down the last 4. 12 goes into 24 twice. 2 times 12 is 24. 24 minus 24 is 0. So 112 boxes will be used. Not 12, 112. Printers can be packed 12 to a box. If 532 printers are to be packed, but only full boxes are shipped, how many full boxes will be shipped? How many printers are left over and not shipped? So here we're dividing by 12, but we're expecting there to be a remainder left over and not shipped. So let's do 532 divided by 12. 532 divided by 12. 12 doesn't go into 5. 12 does go into 53. It goes in 4 times. 4 times 12 is 48. Subtract. 53 minus 48 is 5. Bring down the 2. 12 goes into 52 4 times. 4 times 12 is 48. Subtract 52 minus 48, we get 4. Nothing else to bring down. So it goes in 44 times with 4 left over. That means there's going to be 44 full boxes and 4 printers left over and not shipped. Let's talk about finding averages. The average of a list of numbers is the sum of the numbers divided by the number of the numbers. So add them up and divide by how many there are. So if we wanted the average of 37, 26, 15, 29, 51, and 22, we would add them up. And because there's 1, 2, 3, 4, 5, 6 of them, we would divide by 6. That's going to be 180 divided by 6, which is 30. I leave that addition up to you as an exercise to make sure you get 180. To compute a safe time to wait for reactions to occur after allergy shots are administered, a lab technician is given a list of elapsed times between administered shots and reactions. Find the average of the times 4 minutes, 7 minutes, 35 minutes, 16 minutes, 9 minutes, 3 minutes, and 52 minutes. So we would add up 4 plus 7 plus 35 plus 16 plus 9 plus 3 plus 52. And there's 1, 2, 3, 4, 5, 6, 7 of them. So add them up and divide by 7. The sum of those 7 numbers is 126. 126 divided by 7 gives us 18. So the average would be 18 minutes. And that is it for this topic. The topic is exponents and order of operations. The objectives in this topic are write repeated factors using exponential notation, evaluate expressions containing exponents, use the order of operations, and find the area of a square. 3 times 3 times 3. Well, if we had 3 plus 3 plus 3, that would be 3 times 3, repeated addition. This would be 3 to the third because we have 3 3s. Now, of course, I picked the most confusing example to start with, where the normal size number and the little floaty number are the same thing. So how about I do something like this? 3 times 3. Well, 3 times 3 can be written 3 squared. Now the numbers are different. The number that is repeated is what we call the base. And that little floaty number is called the exponent. So the base is multiplied together a total number of times equal to the exponent. Since we have 3 times 3, 2 factors of 3, the exponent is 2. What about 5 times 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 5? 1, 2, 3, 4, 5, 6, 7, 8, 9 total factors of 5. Well, the base would be 5 and the exponent would be 9. So we've taken something written in standard notation and we've changed it to exponential notation. So exponential notation is actually very useful for us to take a big long list of multiplication and sort of simplify it a bit. They don't all have to be the same number in order for us to benefit. look at this list. 7 times 7 times 5 times 5 times 5. Well, this part here would be 7 to the second power. And by the way, the little floaty 2, I think I said it before without explaining. Is called squared. When we see the little floaty 2, or we could say to the second power, you'll hear exponents referred to as powers as well. Remember when we did area and I said inches times inches is inches squared? Well, 7 times 7 is 7 squared. When we multiply something by itself, we give it that second power. We say that it is squared. So that's just a little explanation about what I'm saying. And I owed you that explanation for square inches, inches squared. And I figured 7 squared was a great time to do it. Times 5 times 5 times 5, that's 5 3 times. 5 to the third power. And this has a special name too. So we'll either say to the third power, or we'll say cubed. And now, have you ever heard of cubic feet? Have you ever heard of cubic inches? Cubed is what we get when we multiply something by itself a total of 3 times. So something like volume, which is length times width times height, would be inches times inches times inches, which would be inches cubed. That's what a cubic inch is. It's a cube. That's 1 inch all around, a cubic inch. But anyway, to the third power, you'll hear me say cubed. You'll refer to it as cubed or to the third power. And look, 7 squared times 5 cubed is this right here. You might want to write times like that. We're going to get out of the habit of doing that. We're going to start using dot for times because at the end of the course, we're going to start doing algebra, and algebra has x's. And when you multiply x's times things, you don't want to get confused with x, the letter, and x, the times symbol. So please use the dot for multiplication, or you can also use a star. But you'll see me using dot. So 7 squared times 5 cubed would be a way of writing this using exponential notation. Let's do another one. 8 times 3 times 3 times 3 times 3 times 3. Well, we don't have any repeated 8s, so that's still just 8 times. And then how many 3s do we have? 1, 2, 3, 4, 5. 3 to the 5th power. And no, there aren't any special names past squared and cubed. Maybe in some dimension where the creatures there could understand what the 4th dimension is, length times width times height times what. When they give that a name, maybe they'll apply it to the 4th power there, assuming that their math is the same. Let's go again. 7 times 2 Waiting for my hand to catch up. There we go. 7 times 2 times 2 times 2 times 2. 7 times 2 to the 4th power. How about this one? 4 times 4 times 5 times 7 times 7 times 7 times 7. Well, there's 4 squared times 5 times 7 to the 4th. And by the way, since there would only be one 5, we could also write 5 as 5 to the 1st. The problem is 5 to the 1st can be easily simplified to just 5 itself. So we don't put the 1 in our final answer. But just know if we don't see an exponent on a number, there is an implied exponent of 1, not 0, 1. Okay, now instead of just writing things in exponential notation, let's actually find the value. So how do we find the value? First, we unpack it. Think of this like a zip file. You have to unpack it to actually see what's inside. And 8 squared means 8 times 8. So a factor of 8, a total of 2 times, 2 factors. And 8 times 8 is 64. The squareds are actually in your multiplication table that you can make. Write down the diagonal. There we go. Just barely ran out of room. 1 squared is 1, 2 squared is 2, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, and 9 squared is 81. Write down the diagonal. Because it's 1 times 1, 2 times 2, 3 times 3, and so on, all the way to 81, which is 9 times 9. Now, they're not all going to be in your multiplication table. 7 cubed, for instance, that's 7 times 7 times 7. 7 times 7 is 49, and then we would have 49 times 7. Again, sorry about my current internet connection. I'm going to try to keep an eye on what's going on over here. If it freezes up, I'll give it a second to catch up, re-explain what was happening. But I'm talking it through. That seems to be going okay. 7 times 7 is 49, and then the 49 times 7, which we'll do by hand. 49 times 7. 7 times 9 is 63. Carry the 6. 7 times 4 is 28. 29, 30, 31, 32, 33, 34. So 7 cubed is 343. How about something like 3 to the 5th? Well, 3 to the 5th would be 3 times 3 times 3 times 3 times 3. 3 times 3 is 9. Write down the rest of it. Times 3 times 3 times 3. Notice I'm just doing one thing at a time. Then I could do 9 times 3 is 27 times 3 times 3. Then I can do 27 times 3. Then I need to get off the multiplication table. I need to do some work. 3 times 7 is 1. Carry the 2. We'll carry the 2. 3 times 2 is 6 plus 2 is 8. So 27 times 3 is 81 times 3. And this will give us our final answer. 81 times 3. 3 times 1 is 3. 3 times 8 is 24. 243 would be 3 to the 5th. How about 1 to the 12th? Well, 1 to any power is just going to be 1, because 1 to the 12th is 1, 1, 1, 1, 1, 1. 1, 1, 1, 1, 1. 1 times itself, a total of 12 times. But 1 times 1 is 1, times 1 is 1, times 1 is 1. Since anything times 1 is itself, and we keep multiplying by 1, 1 to any power is 1. Now our next one, 2 cubed. 2 times 2 times 2. 4 times 2. 8. This is going to be one that you almost want to know offhand. 2 cubed is 8. 2 times 2 times 2 is 8. That's going to be a very common cube that you'll run into. It's really easy to figure out, but it's also pretty easy to memorize. So 2 cubed is 8. But if you don't memorize it, this is how you figure it out. Another common one is 3 cubed is 27. I'd like to take a look at 6 to the 4th. Now, normally we'd just write this out 6 times 6 times 6 times 6. And we would go 6 times 6 is 36, and then 36 times 6 is whatever that is, and then whatever that is times 6 is the final answer. When it's all repeated multiplication like this, I also want to show you that you can do 6 times 6 is 36, and then over here, there's another times 6 times 6, which would be 36 again. So you can do 36 times 36. 6 times 6 is 36, carry the 3. 6 times 3 is 18, 19, 20, 21. 3 times 6 is 18, carry the 1. 3 times 3 is 9, plus 1 is 10. Add 6, 9, 2, 1, and get 1,296. This is the same as if you would have done 36 times 6 is 216. And then 216 times 6, 36, carry the 3. 6 times 1 is 6, 7, 8, 9. 6 times 2, 12. 1,296. So you get the same answer either way, straight across or grouping 2 and 2. So that's a little trick you can do with the fourth power. That makes a difference for something like 3 to the fourth, where 3 times 3 times 3 times 3 can give you 9 times 9, which can get you 81 pretty fast. You don't have to do 9 times 3 is 27 and then have to do 27 times 3 by hand to get to the 81. So sometimes this grouping you can do with fourth power or even sixth power. Add another times 9 and you have 3 to the 6th. But we can only do that because it's all multiplication. We're going to see after the break that if we have different signs in here, mixed up, adding, subtracting, multiplying, dividing, there is a certain order that we have to do those operations in. It's called the order of operations because math people, they're really smart with the naming. Let's take a look at something like 10 to the fourth power. 10 is a very special base. In fact, base 10 is what our entire number system is based off of. 10 to the first is 10. 10 to the second is 10 times 10, which is 100. 10 cubed is 10 times 10 times 10, which is 1,000. 10 to the fourth is 10 times 10 times 10 times 10, which would be 100 times 100, which would be, remember our trick with numbers that end with 0. We can cut them off. 1 times 1 is 1, and then put on the 1, 2, 3, 4 zeros. Look at that. 4 zeros in the answer, and it's 10 to the fourth. 10 to the fourth has 4 zeros. 10 cubed had 3 zeros. 10 squared has 2 zeros, and 10 to the first, just 10, has 1 0. So 10 is a very special base. The exponent just tells us how many numbers to put on there. So 10 to the seventh would be 1 with 1, 2, 3, 4, 5, 6, 7 zeros. 10 million. So 10 is a special base. And of course, I mentioned before that something to the first power is just itself, which means 1 is a special exponent. Anything to the first power is just itself. So I made a point of saying those diagonals, those diagonal numbers, 1, 4, 9, 16, 25, the squares. They're special. They're important. You should know them. Why should you know them? So that you can quickly and easily tell me that this is 3. So what is this? This is something called a square root. The symbol itself is called a radical, but when it's just this radical symbol, it means we want the square root. Notice that 9 is 3 squared, 3 times 3. A square root gets rid of the square. They're inverses. They undo each other. So if the square root of 9 is the square root of 3 squared, the square and the square root get rid of each other and just leave us with 3. A square root is the number times itself that will give us whatever is underneath the radical, whatever is underneath the square root sign. So the square root of 25 would be 5. Why? Because 5 times 5 is 25. That means 5 squared is 25. That means if we take the square root and the square cancel each other out, and we're just left with 5. So you should know these. The square root of 81. Well, 9 times 9 is 81, so the square root of 81 is 9. Basically, the square root of anything along that diagonal. 1 times 1, 2 times 2, 3 times 3, 4 times 4, and so on. You should be able to recognize those square roots. What if you get something like this? The square root of 121. Well, we only know as high as 9 times 9 is 81 off the top of our heads, and technically we know 10 times 10 is 100. So multiply from there. What's 11 times 11? Well, sure enough, 11 times 11 is 121. So by what we mean by square root, what times itself gives us what's underneath, that would be 11. What would be the next square root we could take? Well, 11 times 11 is 121. 12 times 12, that is 144. That means the square root of 144 is 12. And for the purposes of this class, anything in between, like the square root of 130, you're not going to be asked how to do because you need a calculator or a lot of time to do it by hand without. So anything you'll be asked to find the square root of is a perfect square. For the purposes of this class, at least. When you move on to future courses, there's going to be more things you learn about how to find and simplify those ones in between. We want to write these expressions using exponential notation. So in number 1, there are 4 factors of 8. That would be 8 to the 4th power. In number 2, there's 3 factors of 3. That's 3 to the 3rd power. Illuminating, isn't it? In number 3, there are 5 factors of 10. So 10 to the 5th power. And then in number 4, we have 2 factors of 5 and 1, 2, 3, 4, 5, 6 factors of 4. That would be 5 squared times 4 to the 6th. We can go the other direction to evaluate exponential expressions. 9 squared, we would write that as 9 times 9, which is 81. 4 to the 5th, we would write as 4 times 4 times 4 times 4 times 4. 5 factors of 4. And if we multiply that out, we get 1024. 4 times 4 is 16. 16 times 4 is 64. 64 times 4 is, I think, 256. Times 4 must be 1024. In number 3, 5 times 3 squared. We would not do 5 times 3 is 15, and then 15 squared is 15 times 15. That 5 is to the first power. There's no power on it at all. And when there's no power, that means there's one factor. One factor would be an exponent of 1. So this is 1 5 and then 2 3s. In other words, 5 times 3 times 3. And the associative property says it doesn't matter how we group that, so we can do 5 times 3 is 15. 15 times 3 is 45. Or we could do 3 times 3 is 9. 5 times 9 is 45. Wouldn't it be nice if there was a special rule that said we would do the exponent before the multiplication? A rule that specifies, hey, don't do 5 times 3 is 15 first. It turns out we have just such a rule, and that rule is called the order of operations. When doing the order of operations, step 1 is to perform all operations that are within parentheses or brackets, or other grouping symbols such as fraction bars or square root signs, starting with the innermost set. So if there's parentheses inside of parentheses or parentheses inside of brackets, we go to the innermost set and start there first. The second step is evaluate any expressions with exponents. The third step is multiply or divide in order as you come to it from left to right. The fourth step is add or subtract as you come to it in order from left to right. Some people misunderstand the order of operations. A way to remember it is please excuse my dear Aunt Sally, parentheses, exponents, multiplication, division, addition, subtraction, PEMDAS, PEMDAS. So PEMDAS, please excuse my dear Aunt Sally, helps us remember. Parentheses, exponents, multiply, divide, add, subtract. But that makes people think that we have to multiply before we divide and that we have to add before we subtract. And that's not true. The multiplication and division happens in one step from left to right as we come to it. That means division can happen before multiplication. Likewise, addition and subtraction happens in one step as we come to it, left to right, which means subtraction can come before addition. I speak the truth, believe me. Okay, let's simplify. 2 times 4 minus 3 times, or sorry, minus 3 divided by 3. The first thing we would do is work inside of parentheses or other grouping symbols. There are no parentheses in this problem. Well, then we'd take care of any exponents. There are no exponents in this problem. Then we come to multiplication and division. Multiply and divide from left to right as we come to it. So from left to right, the first thing we hit is 2 times 4. So do the 2 times 4. That becomes 8. Copy the rest down. Then we have 8 minus 3 divided by 3 from left to right. We're still on multiplication and division. We would divide 3 divided by 3. So 3 divided by 3 is 1. Copy the rest down. Finally, 8 minus 1 is all we have left. 8 minus 1 is 7. So we really kicked it up a notch here. 4 to the third plus square bracket 3 squared minus parenthesis 10 divided by 2, close parenthesis, close square bracket, minus 7 times 3. Well, we have grouping symbols. Not only do we have grouping symbols, but we have grouping symbols inside of grouping symbols. Go to the innermost set. Inside of that, we have 10 divided by 2. 10 divided by 2 is 5. Do that and copy the rest down. Looking at what we have now, we have one set of grouping symbols, the square brackets. Inside the square brackets, we have exponent, we have subtraction. Order of operations would have us do the exponent first. 3 squared is 9. To finish off inside the square brackets now, 9 minus 5 is 4. I'm only doing one thing at a time and copying the rest down. Now looking at what we have no more grouping symbols, but we have an exponent. 4 to the third. That's 4 times 4 times 4. 4 times 4 is 16. 16 times 4 is 64. 64 plus 4 minus 21. Why minus 21? Because of 7 times 3. Once we took care of that exponent, the next thing would be multiplication. So we hit that multiplication problem 7 times 3 after we changed the exponent 4 to the third to 64. But if you wanted to make that 2 separate lines, if you wanted a line in between there that said 64 plus 4 minus 7 times 3, that's perfectly fine. The more steps you write, the less likely it is that you're going to make a mistake. So the more steps, the better. Finally, we add or subtract as we come to it from left to right. 64 plus 4 is 68. 68 minus 21 is 47. You get anything but 47, you've done something incorrectly. Very likely followed the order of operations. Next up, we have a division bar with 6 plus 9 divided by 3 on top and 3 squared on the bottom. We'll take care of the top and bottom separately. That counts as a grouping symbol. Groups the top as one thing, groups the bottom as something else. On top, we would do the division before the addition. So 9 divided by 3 is 3. On the bottom, 3 squared is 9. On the top, 6 plus 3 is what we're left with. That's 9. Finally, since we've simplified the top completely and gotten 9, simplified the bottom completely and gotten 9, 9 divided by 9 is 1. Find the area of a square whose side measures 4 inches. So a square is just a special rectangle where every side is the same. This might not look it, but since it says it's a square, all 4 sides are 4 inches. Area is length times width. That would be 4 times 4 in this case, which would be 16 square inches. But the reason we're looking at this right now is that since it's a square, since it's 4 times 4, it's always going to be side times side. Length times width, length and width are going to be the same in a square. So instead of length times width, we can say that the area of a square is the side squared. Anything times itself can be expressed as a square. So this would be 4 inches squared, or 16 square inches. And that's it for this topic.